All right. Good afternoon. Welcome to the seminar series for April. We'll just give it another minute so that people can join in. All right, I have 12:02, so we're going to go ahead and get started. Hello, everyone, and again, welcome to the April seminar series. My name is Jarma Bennett, and I'm a Senior Water Resource Control Engineer with the State Water Board's Office of Information Management and Analysis. Thank you for attending today's seminar. All seminars are open to the public and recorded for posting in the details of the corresponding events on the College of Water Informatics events webpage. There will be a question and answer period at the end of the talk, so please hold your questions until today's speakers have finished their presentation. Everyone except the speakers will be muted until this time to avoid disturbing the talk. During the Q&A session, we will post a very brief survey, so please make sure to fill it out so we can improve the seminar series experience. We are adjusting our communication routes a little this time. We will continue to use Zoom's Q&A feature for questions about the presentation, but we are also enabling the chat feature for all participants to share relevant information. But again, if you're wanting to ask a question of the presenters, please use the Q&A feature. Today, we're lucky to have a team of presenters. They are Dr. Bethany Robinson, who works in the Regulatory Development Unit of the Division of Drinking Water at the Water Boards. Bethany researches and develops regulations for drinking water contaminants. Dr. Scott Coffin, who serves as a research scientist, also in the Division of Drinking Water at the Water Board. He performs research and develops drinking water regulations for microplastics and other contaminants. Scott's expertise includes data science, ecotoxicology, and human health risk assessments. And Dr. Mariel Pinheiro, a research data specialist with the Office of Research Planning and Performance. Mariel works on a variety of data-driven efforts for the State Board, including water affordability and the development of water use objectives for urban water suppliers. With that, please welcome the presenters.
Thank you, Jarma. So we're really excited to present this today. It was a it was a massive effort that had to be sort of put together very fast, and this wouldn't have been possible without the help of a lot of staff, both on the water board side and on the local agency side. So just wanted to acknowledge that up front. There you go. Okay. We will be going through a number of different topics throughout this presentation because a lot went into this project. We'll discuss how we designed the survey, so what type of data we wanted to obtain, but also additionally how to ask the question in a way that would give us the most useful information. We needed to figure out how many systems we needed to collect data from and also how to distribute the survey. And then we'll talk a little bit about how we analyzed the results, how we used correlation and regression and imputation to fill in any missing data that we had, and then to extrapolate statewide and provide confidence intervals for those numbers. So just a bit of background. After California went into shelter in place in March, the Executive Order N4220 halted most water shutoffs due to non-payment during this time. In order to get a sense of the subsequent impact to water agency finances as the result of the moratorium, ORPP conducted a voluntary survey in June of 2020 and then collaborated with DDW in November to collect data from a wider range of systems. So the goals of the survey efforts have been to understand the impacts of COVID-19 and the corresponding shutoff moratorium, both to the water systems, but also to their customers. This data has helped to inform some preliminary estimates on the financial impact and sort of help us estimate the total overall volume of statewide debt and revenue shortfalls. So, first survey was conducted in the form of a Shiny app that used MongoDB as a backend to store responses, since Shiny apps don't usually have actual storage capabilities. They're usually for visualizations rather than data collection. Since the survey was voluntary, we really relied on the listservs and the help of some of the water agency organizations to really to get the word out and to try to collect as much data as possible. It did give us some useful insight into the initial impacts over the first few months of lockdown, but we couldn't really use this data to extrapolate statewide. The sample was heavily skewed towards larger systems and specifically the Los Angeles area. And overall, it only represented about a third of the state's population. So our second effort was going to require a lot more pre-work if we wanted to get usable data. We needed systems from all different sizes represented in the data set and enough responses to be able to give us confidence in our statewide estimates. Therefore, we split the total list of community water systems into two categories: those with less than 10,000 service connections, which we'll be referring to as the small systems, and those with more than 10,000 service connections are large systems. The split is necessary because the larger systems tend to have a bigger buffer for budget shortfalls. So note that the small systems make up about 92% of the total number of systems, but the larger systems serve about 82% of California's population. So the survey results covered 428 small systems and 151 larger systems, with some agencies providing responses for multiple systems within their service area because they weren't really able to split up the numbers in their billing software. So unlike the summer survey, where we relied on the agencies to go to the site and complete the forms themselves, Water Board staff reached out to the selected systems directly. DDW staff were in charge of the small systems. They called system administrative contacts and filled out the forms on behalf of the systems. The large systems were directly emailed the forms and then returned them to the ORPP staff. And now I will be turning things over to Bethany to explain how we went about selecting the systems and designing the survey questions.
Thank you. On to sampling and survey design. Next slide. So we had several different options when it came to sampling and probabilistic sampling. We could either completely sample randomly, which is simple random sampling. We could sample randomly based on strata, or called stratified random sampling, or we could sample in stages. So for us, next slide, stratified random sampling was best for this situation, specifically because these water systems are so incredibly different at different service connection sizes. So we have, here we're looking at just the small and medium systems, and we're looking at the bins that we eventually put them into. But you could see how in each of these bins, these systems have their own statistics and they have their own characteristics. And within each of these, we have the small and medium water systems. And then within those, we have the disadvantaged small and medium systems. So it was really important to us to make sure that we sampled representatively from each of these systems and make sure that we could represent all of these systems with our data at the end. Next slide. So to do this, we kept the populations of the large and small water systems completely separate. For the small and medium systems, we divided them up into 4 bins using Jenks natural breaks. Now, this is a way to divide up data based on how it is statistically similar. So we played around with a number of bins, but eventually we landed on 4 bins because it divided the water systems best into the most similar bins. And then for the large systems, we just randomly sampled those by population, and those were stratified by service connections and by region. In addition, we also had 5 voluntary responses from the large systems. So when we ended up binning these, you could see that where the breaks are. And each of these was divided up so that we could make sure to get the characteristics of the systems in each bin, because they're very different when you're looking at a system with only 100 service connections or when you're looking at a system with close to 10,000 service connections. Go ahead and go next slide. And specifically, we wanted to make sure that the margin of error for these different bins was similar. And so here you could see after we got our sample from the population, we calculated the margin of error, showing that it's similar among each of the bins, which was what we were trying to do with the Jenks natural breaks and the stratified sampling. So good there. Next, go on, Marielle. So when we designed these questions, there were a lot of considerations we need to think about. We needed to look at the number and length of questions. There were a lot of limits, as Marielle already said, on staff time, both water board staff and on local agency staff. There was also the issue of data availability. Some billing systems didn't allow them to answer the questions that we had. They didn't allow them to go back and look at historical records. And some systems just didn't want to participate at all. And billing cycles were also different between different systems. Some were monthly, some were every other month, some were every 6 months. And so we had to take the data from these systems and make it uniform so that we could compare it across all of the systems. We also had to make sure to protect any personal identifying information and to make sure that we had guidance documents for staff so that all of these questions were answered consistently across the entire state of California. Next slide. And so there were 2 categories for each of the small and medium systems and then for the large systems. For the small and medium systems, we focused on system finances, which included revenues, expenses, cash reserves, and the months before assistance needed. And we also wanted to look at household debt distribution. So how many accounts had debt? What is the total amount of that debt? And then what does it look like on a per zip code basis? Can we actually get this and more geographically distributed? And then for the large systems, the first set of questions was on household debt. How many delinquent accounts? What are the debt levels, the total debt? And then also per billing cycle and divided up into zip codes. And then we also wanted to know about fees and repayment options. What are the late fees? What are the number of accounts on repayment plans? Next slide.
All right, so now we're going to be going into how we actually went about collecting and then like sort of aggregating all of the data, as well as putting it into a form that could then be released publicly. So for legal reasons, I wasn't able to use that Shiny app that I'd built the first time. And because we were working on an extremely short time frame, we couldn't build an entirely new site from scratch. So I had to think about what platform would be flexible enough to handle all of the various question types that we'd come up with, but also familiar enough to the staff and the agencies that would be filling out the form. Additionally, I needed to make sure that the responses would be in the right format so I didn't have to go through and do a ton of data cleaning. As an example, like some programs, they'll interpret any number that contains commas as a string rather than a number, which means that if you try to do any sort of numerical operations on it, it'll just produce gibberish as output. I needed to be, whoopsies. Why did that happen? There we go. I needed to be sure that the data was going to be consistent across different billing types as noted before, and also that I would just be able to write a program that would be able to take all those forms, just pull all the answers out, and then stick it into a single database. So Excel was the final solution. It was in the form of a spreadsheet with data validation to make sure that we would be sort of controlling the responses. So like if it was a yes/no question, they would, provide only one of two responses, for example. Excel's been used for similar purposes before, such as the water loss audits that DWR conducts annually. So I had some working examples that I could use when I was building it. Excel does have a lot of advantages to it for me. I was able to create a layout that had tabbed sections for each of the various like subcategories. I could do multiple choice. I could do tables all in one space. I didn't need to learn JavaScript in 2 weeks, and it would be able to differentiate between numeric and string just all on its own. So I created separate template files for the large and small system responses because we were asking slightly different question subsets, and then used Python to automate generating a survey form for each agency. So these are some of the examples of how we asked the questions. We had like yes/no questions. We had multiple choice. We had comment boxes where people could provide context for like some of the responses that they were giving. And then we had tables where people were providing information on things like their expenses and revenue for 2019 versus 2020 per month and then total. And this is one of those areas where we're able to differentiate between monthly versus bi-monthly or whatever, because if it was bi-monthly, they'd only provide answers every other box as opposed to every box in the table. And then because we wanted to have a spatial component to the data that we were receiving, we asked the respondents to bin the number of delinquent accounts in each zip code with their service area according to the amount of debt per account. So if you had, a lot of the smaller systems, they only had one zip code, that was fine. But some of your really, really big agencies, they might have as much as 30 zip codes. And so this was really, really useful, like interesting information. It provided us the ability to join the data later on with the zip code level American Community Survey data. And so we were able to look at not only spatial trends, but also connect some demographic data to that as well. All right, now on to how I created those individual forms. So in the S drive, I had separate file trees for the small and large survey responses, which are shown in the diagram to the right. There was a main folder and then like a subfolder for each district, and then a folder for the incomplete surveys, the blank ones that I would be creating. And then once they were finished, then they'd be moved to the completed folder. So I used a library called OpenPyXL to fill in the template cells. And so with a combination of CIDWIS and data from the electronic annual report, I was able to pre-fill in the public water system ID, the system name, and the billing cycle length for each of the systems that we were going to be asking the questions to, and then saved the files in the appropriate subfolder with a very standard naming convention, survey, district number, PWS ID number, and the name of the system. And then, like I said, staff would go into the S drive, they'd take an incomplete form, they'd contact the system, they'd fill out the information, and then once it was complete, it'd be moved to the completed folder. And that's what I scanned when I was doing the final data extraction and compilation. So this diagram here sort of shows the main workhorse function that I created using OpenPyXL and Pandas. So I took the input Excel file and a dictionary that contained the variable name that I was going to call the response, and then the cell that it was located within. And then I would open each file for each variable name in the dictionary. I would extract the value that was located at that cell, and then I would store it in an output answer dictionary. I also stored the file path just in case we needed to go back and like double check any answers. And then on that zip code table tab, that was really easy. All you do is you use pandas to just read the table in its entirety. You can also store that in the dictionary because dictionaries are very flexible. And then the function would return that entire output dictionary. So then finally, it was just a matter of taking all of those individual responses and putting them together. Because we were going to be releasing the data set publicly, we needed to anonymize the responses as best we could, but still needed to have a record of who had provided those original responses for our own note-taking purposes. So I had a table that had like a key list. I created a 3-digit ID for each of the survey responses, which corresponded to each of the surveys, but I kept track of, like what system and what PWSID it was. In the public release file, then it had that 3-digit ID, but it didn't contain any of that identifying information. We also had some help with going through and like redacting anything in the comments that would make that information possibly identifiable. But we also stored the original information with the ID, the full data, and that original file name that was stored on the S drive. So I used the I don't know how to say that, but I'm just going to PyODBC to write the data to SQL. I got some server space to do that. And then if we ever needed to change anything, I would just be told, hey, we found something, we resaved the file, can you just change it? All I had to do was like go back to that file, reread it using that function from the previous slide, and then like search the ID value and then like change the values in that table. Also adding any notes to the corrections that were made. And then if I ever needed to get that data again, I used a combination of the read SQL query function in pandas and then the to Excel function in pandas to write that data back out to Excel, which then we could use to distribute it to the public. Okay, now Scott, it's your turn.
Thanks, Marielle. So once we receive the data, there's a bit of analysis that you need to do to make extrapolations to statewide. So you can go to the next slide. So here I superimposed two distributions. The first is the sampled data that we had, the water systems based on their median 12-month household income on the x-axis. And then in the yellow distribution is the actual population. And you can see that these distributions, while they overlap quite a bit, they're not exactly the same shape. And so in order to make extrapolations from the data that we received from the water systems that we did sample to the greater population, it's evident that we needed to do some additional modifications to reliably extrapolate. So the basic workflow for this is on the next slide. And this is a pretty generic workflow from a statistics point of view for survey analysis. One of the things that is a bit unique that we had to do was the first step, which is imputing the missing data. So despite our thorough attempts to get as much clean data as we possibly could from these water systems, as Marielle explained, you never get the data that you want especially when you're under these really tight time crunches and priority projects like that we were under for COVID-19. And so we didn't want to throw out the data that was incomplete, because that information is useful, and so we performed some steps to impute this missing data using statistical analyses. The next step is calculating the base weights, which is really simple, just looking at the proportions of systems that you sampled versus the population. And then we had to adjust for those that didn't respond to the survey. And then finally, we had to calibrate the weights. So in the next slide, I'm going to talk about the weighting. So that this is the base weighting. This is a very, very simple formula. Basically, the base weight is just the proportion of systems that you sampled versus the population. And so everybody gets one number for this. It's the exact same number. And since we stratified, we had 4 different strata. They actually got the same number within those strata, but they're different within the strata. Basically, when we design the survey to be stratified, each strata we consider its own unique survey, its own population. And so you can only extrapolate from systems within that strata to the greater population strata. Next slide. So now I'm going to talk about the imputation, which was really, again, necessary in order for us to actually use the data that we received. On the next slide. This is an overview of like some of the reasons that we had missing data. Some of this was sort of discussed before with these limitations, both on the systems that we queried. You know, a lot of them just didn't have the historic data, as well as you know, some time limitations with the survey. So overall, a lot of systems gave us enough information that we could make reliable estimates of the missing data. And I'm going to go over that in the next slide. So on the next slide, there's a heat map. And this is a way of visualizing the data that's missing all in one heat map. And so blue, data's there, red, we didn't get a response for that question. And you can see that there's some blocks where we just didn't get information for those questions for nearly everyone. For those data, it's really difficult to impute, and I probably wouldn't impute it because you're just missing that entirely for systematically. But you can see for other questions and water systems, it's more sporadic, and you actually have a lot of data for some, and then for some questions for some water systems, but then you don't have data for other questions for the same water system, which is the perfect scenario for multiple imputation. If you go to the next slide. So before you impute data, you should understand the types of missingness that data can be. There's really only 3 types. And the first is missing completely at random. And this is basically the data is missing and you cannot explain it. It's just perfectly random. The next is missing at random. And this is, there's some level of, there's some pattern to the missingness. The propensity of the missingness depends on things that you can quantify. So for instance, some data may have been missing more for groups with lower income than higher income. This would be a missing at random, something you can predict. And then the missing not at random, this is when the data is missing, but you can't explain it. It correlates with unobservable characteristics. At this point, you wouldn't want to do any imputation with missing not at random because you can't form a hypothesis for why it's missing. So the first 2, missing completely random and missing at random, you're good to go for imputation. Next slide. So to determine what type of missingness we had, we looked at the strata that we'd set up, these 4 different bins that were really based on the size of the system, but they also tended to correlate with the economic status of those systems, the disadvantaged status. And the missingness fraction, the darker color here in this heat map, correlates to higher missingness. So you can see for the reserved or the restricted cache reserves, bin A had the most missing data, and bin D had the least missing data. And actually, you see a decreasing trend in missingness as you increase the number of service connections in the bins. And so this shows us that the data was missing at random in a predictable way, and it was probably correlated with the size of the system, which is also correlated with the socioeconomic status of that system. Next slide, please. So these are the basic steps that you go through for multiple imputation. First, you examine your incomplete data, then you impute the data. This is an iterative process. So on the next step, you analyze the results, and if you don't think that the imputed data matches really well with the available data, then you go back and you try and re-impute using a different method, or you throw it out. And then you're left with your final pooled results, which has both imputed and real data. Next slide, please. So like I mentioned, there's a lot of different methods that you can use to impute your data. The basic scheme is these data are predictable by other metrics that you have. So for instance, the cache reserve on the y-axis is predicted by the unrestricted cache reserve. Almost perfect linear correlation for looking at some of these groups. Obviously, there's like some deviations here, and so a linear model is the most basic way to predict this. But we use much more sophisticated techniques using machine learning, random forest modeling. On the next slide, you can see what these imputed data look like when you superimpose them on the observed data. And this is that step that I mentioned where you really want to analyze the imputations and make sure that they're realistic. So you can look at these distributions of the different imputation iterations are in red, and then there's only one line for the blue, that's the actual observed data. And you can see that some of these imputations resemble the distribution better than others. And so that's where you want to really tune your model and make sure that you're not overfitting the data, but you also want to make sure it simulates the data as best that it can. So you choose the best imputation, and that is your full data set. Next slide. So now that we have a complete data set, we can calculate the base weights, which I mentioned before is really just a proportion of the water systems that we sampled versus the population. On the next slide, we re-examine these bins that we set up. First strata has 1 to 10,000 or 1 to 1,000 service connections, and then we have some more bins above that until we get to 10,000. And so each of these gets their own proportion relative to all of the water systems in the whole state. So in the next slide, now that you have your base weights, you have your full data set, then you need to adjust for non-response. So a lot of this stuff, the non-response, the imputation, the weights, none of that would actually be, you wouldn't have to do any of that if you had perfect data. So if everybody that you wanted to monitor, that you wanted to survey, gave you full responses and you didn't get any volunteers and there were no missing data, then you wouldn't have to really do any of this. You would just stop, you would calculate your base weights, and that would be your final weight. But as many of you know that have collected data, it never goes according to plan. And so that's why we have to do a lot of this cleanup post hoc. So on the next slide, you can see that the responses from the water systems was also not random. We received more responses from bigger systems. So on bin D, you can see the response rate was nearly up to 90%. And then for bin A, it was just hovering around 80% response rate. And this is really to be expected because these smaller systems, they don't have nearly the staff capabilities. They may not be able to, might not be available when the water board staff called. And so we just received fewer responses overall. There was also a lot more in that bin, 184 in bin A versus 56 in bin D. And so you can't really compare these if the response rate was different. So we had to make an adjustment for this. So on the next slide, you can see the non-response weight is really just the proportion of water systems that didn't respond in the bin. And you can model you can adjust this non-response weight based on different characteristics of the systems. So it's not just the being in the bin that determines someone's non-response propensity. There's additional factors that we have available called auxiliary variables. So one of the best predictors that we found for non-response was socioeconomic status of the community that the water system serves. On the x-axis, you can see the median 12-month household income. You can see it's a bit of a wonky relationship, but again, that's why we used much more sophisticated statistical techniques. On the next slide, you can see we actually used type of decision trees. This is a single decision tree that looks at the data from different variables and runs a regression at each step. And then when you get to the next step, it runs another regression and eventually puts the water systems into different bins at the very bottom. And each bin is a probability of responding to the survey or not. And then that becomes the survey weight that we adjust to. And do this, make 1,000 of these decision trees, and then take the average of them, the composite, and that's a random forest. And so that's what we did to predict the response propensity. Next slide, please. So we've imputed our data, we've calculated the base weights, we've adjusted those weights for those water systems that we wanted to get data from, but they didn't respond. And then finally, we have to do something which is calibrating the weights to the greater population so that we can get the most representative survey data possible. Next slide, please. Calibration, very similar to a lot of the steps that we talked about before. You look at the variables that you have available. We know how many service connections every water system has in the state. This is an auxiliary variable that is highly predictive of additional factors, including socioeconomic status. The next slide, you can see some of the other candidate variables that we considered in our analyses. So not only, so you can see the Pearson R value is the number here, and then the asterisks are the statistical significance. So looking at the top left, service connections is the distribution, and then that looking how it corresponds with the number of delinquent accounts, which is the middle histogram. You can see there was a Pearson R of 0.73, an extremely significant correlation. And then the total cash is also extremely significantly correlated to both of these variables. And instead of just using like one variable to predict another thing, we built a more sophisticated model. And then we were able to generate calibration weights that we further adjusted our weights to project statewide extrapolations. So on the next slide, you'll see the impact of both the imputation and the calibration. So on the left is if we just took the data raw, no weights, no base weights, no imputation, and we tried to estimate the total delinquent amount in US dollars, which is the debt. This is the total debt experienced from COVID-19 in 2020 from the water systems that we surveyed. You can see if we weight the data based on our base weights, then we get a much higher estimate. Now we're talking nearly $1.5 billion in debt. But we know that a lot of systems didn't respond that probably have lower debt. So when we adjusted for the non-response, you can see it's lower. And then when we further calibrate by different predictive variables, eventually we get extremely high confidence in our final estimate of debt, which was about $750 million. And you can see that the difference of the imputation here was minor overall, but it did give us a slightly higher number because we could use more data. On the next slide, I'm going to hand it back over to Bethany, who's going to give some insights into some further analyses that we made with this data.
Yes. Was this me or Marielle?
Go for it.
Okay. So when we looked at the total statewide household debt from March to October 2020, here are our survey totals first for the large and medium small systems, and then the statewide estimates. So this was all done just as Scott described. And again, weighting greatly reduced the error bounds compared to the initial estimates. Next slide. So one of the questions that we asked the water systems was, how many months can you go until you think you need outside assistance? And so this, we're calling it perceived assistance. How long do they think they can go before they need assistance? And we wanted to see what variables in our data could predict this perceived assistance. And so we used a random forest machine learning algorithm of 10,000 trees and looked at the variable importance of that analysis. And so the first step was really just throwing all of our data at this and seeing how it shook out. And this was done in rounds where we took off the least important variable each round and then continued trying to figure out which set of variables gave us the best prediction. And essentially that best prediction was just using the median household income and the service connections as shown in the plot on the right. So median household income is on the x-axis and service connections is on the y, and the colors of the dots correspond to how many months they think they can go before they need assistance. So red being 0 to 3 months right away, and all the way to blue being more than 12 months. And so you can see that this, the hotter colors are further to the left with a lower median household income, but that's not always true. And again, this is because this is perceived data. So essentially we're using quantitative data and trying to predict qualitative data, which is a little bit confusing, but it works. Some of the interesting things that came out of this were some of the other rankings. So once we got past median household income and service connections, which we kind of expected, the next most predictive variable was the renter income percent. So what percent of your ratepayers are renters rather than homeowners? And then next was the total cash reserves of the system, and then the CES score, which is a pollution burden score, followed by population. And so because population is so correlated with service connections, we really expected those to be together, but this is showing us that some other factors might be even more important than the total population. So this was more of an exploratory analysis that we did with this data because we wanted to see if it was possible, if we could predict which systems would need assistance sooner, then we could go contact those systems proactively. So it looks like median household income and service connections, as well as renter income percent, were the most important. Next slide.
Okay, so one of the tasks that we were assigned was sort of trying to figure out a way to identify which systems were in the most immediate need of assistance. And you can look at it a variety of different ways, but you might get different answers depending on which variable you're using. I talked a little bit with some folks at UCLA, and they suggested trying to create an overall score based on a number of variables that we had available. And so we used 3 variables to create an overall score. The first one being how many months before they thought they would need assistance, financial assistance. The second being how many days of unrestricted cash on hand they had, i.e. how many days they could operate with just whatever cash they had in their reserves, and then also the revenue to expense ratio. So the metrics that are in red, those are sort of, they signal that the system is probably in the most immediate need of financial assistance. And so when you go through and sort of assign these metrics with sort of like subscores going from 0 being the least at risk and 5 being the highest at risk, and then counting it up. Systems with 2 out of 3 high risk indicators had high financial vulnerability, and systems with 3 out of the 3 high risk indicators had extreme financial vulnerability. So what does that look like statewide? Well, as of November, we found out that about 10% of the survey was at higher extreme risk. And when you extrapolate that statewide, it's a little bit higher at about 12%. And so that meant that, you know, like we weren't in dire straits, but there were definitely some systems that we should be reaching out to immediately. And then finally, using that zip code level data that we had, we were able to examine if there were any sorts of trends that we saw in terms of demographics. And so one very striking thing we noticed when we were looking at the data was that zip codes with higher percentages of Hispanic and Black households had a higher percentage of households with some level of debt, higher average level of debt, and a higher percentage of households with very high levels of debt, so above $600. And this was strongly correlated with median household income. All right, we've pretty much reached the end of our presentation. Just sort of reiterating what we went through at the top. We explained how we designed and administered the survey, gave you a little taste of what we did to analyze the results, and presented a few of the results. If you have any further questions, all the data is available online. It's publicly available. If you're interested in finding out further, you can always email me. Bethany and Scott have their contact information up as well if you have any further questions. And I guess we will open it up now. Thank you.
Great, thank you so much. That is really, it seems like many layers to that project that all took a lot of thought by themselves. We do have a question about imputation, the exercise. Scott, you said you'd want to answer this live. Can you take that?
Sure, yeah. So the question is, what are some lessons learned from this imputation exercise that you think could be applied to other data sets, suggestions, warnings, or other thoughts? So if you're using R, the MICE package is the best multiple imputation package out there. It does a lot of the analyses pretty much for you, and it provides a lot of analytics and visualization tools that you can look at to make sure that you're imputing realistically. And one thing that I would caution before you decide to impute your data or not is really think critically about why the data is missing in the first place. If you're looking at like environmental monitoring data and your limit of detection is at a certain range, then you might not want to impute your data below that unless you really understand like the method limitations and all of that. So really think like epistemologically why you need to impute your data before you go towards that step. For this particular application, it was really reliable because we knew a lot about why the data was missing, and we felt pretty solid in our assumptions that we were making with the imputations.
There was also a sort of similar question about calibration, but it's in the chat instead of the Q&A. I don't know, do you want to tackle that one too?
Sure. So the calibration, it really, a lot of the calibration that I did is actually a bit black box, to be honest. Using the survey package in R, there's a calibration function that it uses fairly sophisticated statistical techniques that I didn't have the time to like look into all the equations that were going on, but it was a lot more than just running a correlation. There was, like I said, there was some machine learning involved in that, and effectively what it's doing in like very simple terms is it's just taking the probability, or rather the proportion of the water systems with a certain economic bracket or whatever auxiliary variable in your data set, and adjusting it for what you would expect in the actual population. So if you have an over-representative data set for large or high economic status, which is what we had, then it weights that and it gives that a lower score for extrapolation. But the methods that it does are fairly sophisticated.
Okay, thanks. There's another question that says, this work was clearly very technical for those of us who aren't as advanced in our statistical / data science / machine learning training. What resources, software, or tools would you recommend we look into to get started?
So we did a very good job of making everything sound technical, but a lot of the coding we did came out of packages. And so maybe Scott and Marielle can also talk about the packages they use, but Python is the software that I use, and the Jenks natural bricks came in its own package. The random forest machine learning stuff all comes in the scikit-learn package, and that has like the ability to rank variables by importance, which is what I used. So it wasn't, I guess, very technical coding if you know which packages to go for.
Yeah, so if you know it exists, then you can look for that. Okay. Can any of you speak to how you think this work can and hopefully will support the goals of the water boards in Cali, PA to promote racial equity and environmental justice?
Yeah, so I think just, even just the very tiny little bit of analysis that we did with the zip code data made it immediately clear that there was a disproportionate impact to Black and Brown communities with regards to household debt. And, it's probably gotten worse since this data was collected back in November. And, this is not new. A lot of this, a lot of these trends have probably already been there and were just further exacerbated by the pandemic due to unemployment and the types of jobs that people do and whether or not they were able to work from home as opposed to having to go in. So, I mean, taking this data and joining it to the zip level ACS data and trying to pick apart any further trends, I think would be a very worthwhile effort.
I think that the question of what did you do with your results in terms of next steps, or can you talk a little bit about that? I mean,
so one of the things that we've been sort of trying to figure out, because this data collection stopped in November, is, like it's now April. It's the end of April. Like, what is that? What does that debt look like now? Because even though the shutoffs still, the moratorium is still in effect, those debts are still accumulating. And, once the moratorium is ended, what level of assistance are we going to need? How much money are we going to have to put back into the state? So I have sort of done like a very preliminary exercise to try and estimate what that number looks like and how it's distributed. But yeah, like I said, there's a lot more work to be done.
could you foresee doing a follow-up survey to see how things have changed since November?
I mean, more data is always a good thing, but I'm just a lowly level analyst. Like, I don't have the authority to do that. And like I said, like this was a group effort. This was not just us. Like, we couldn't have collected all of this data so quickly without like DEW staff like really buckling down and just manning the phones like for a couple of weeks. So it would have to be, all hands on deck all over again.
Effort.
But I do think that a follow-up survey would provide incredible benefit beyond just thinking of the direct impacts of COVID-19, because one of the things that we really struggled with were actually coming up with what questions we'd want to ask the water systems. Ideally, we would have had years worth of data on their economic status, because this was just taking a really small snapshot, not even one fiscal year's worth of information, and trying to make inferences from it when we don't understand how they actually manage their funds over the years. And so if we were to repeat this again like this year, then we could actually compare year to year, and we'd be able to build a more sophisticated model for understanding how water systems actually manage their budgets and which ones might actually be at risk.
do you think it would be easier I mean, obviously you've had lessons learned and that kind of thing. Would some of the foundation work that you've done with the first set of survey results help you process the follow-up survey result set?
From all possible angles, it would be easier, I think.
We got another question in the Q&A. Can you take a moment to describe how the study objectives determined the chosen methods? Someone mentioned the exploratory nature of one of the analyses, but it wasn't clear to me how much was exploring data and how much was planned analysis based on questions that drove the survey design.
I think most of the survey was aimed to get certain information about especially statewide debt. So we knew we wanted to extrapolate to statewide numbers, and we knew roughly the information we wanted to get, but it was there was some exploration to be done, especially our question that we did, that I mentioned the exploratory analysis on, which was how many months can you go before you need assistance? That ended, we had planned for that question to basically tell us which systems were in dire need when, and how we could figure out when to help them. But in reality, what we saw is a lot of people thought they were in a lot worse situations than they were. And we ended up using other data to determine their need. And so that was more of an exploration because we couldn't use that data in another like more concrete way. We had planned to use it in a concrete way.
That's good. Okay, I had one more question about the use of Excel to record the survey answers for. It always makes me happy to go back to the tried and true tools, but do you think it limited your kind of the functionality? Maybe you could have made questions required that so it couldn't be missing data if you had some other way to gather that information?
Yeah, absolutely. I think that not being able to make a question mandatory versus voluntary was one of the biggest reasons that we had so many data gaps, because we couldn't like specify which ones we absolutely needed, as opposed to like, you know, which ones would be nice to have but not so much important.
Mm-hmm.
So if I went back and did it again, if I had something more sophisticated, yeah, I'd like that. That'd be great. But
yeah, but no, it looks fabulous for what you did. So that's wonderful. And then the legal limitations of using our Shiny. Can you just briefly talk about that?
Yeah, so the most high-level answer I can give is the first survey effort, the one back in June. We weren't the ones going to systems and saying, please fill it out. They were coming to us and saying, we'd like to provide information. When it's reversed, you kind of need to either mandate it if you're going to like have this thing online, or you have to like do individual one-on-one like responses for every single agency if possible, which was not going to be feasible. So this was sort of a compromise between having, you know, another voluntary survey and reaching out to like every system.
Okay. Well, I think we are coming up to the top of the hour, so we're going to wrap up here, but I would like to thank Bethany, Scott, and Marielle for giving us this really interesting, over my head in some places talk, but that was great. I would like to thank all the attendees for tuning in and engaging in the Q&A today. Keith just added to the chat the link to the feedback survey, so you can give us feedback on our seminar series or suggest future talks. And you'll be able to find the recording of this and other seminar series presentations on the College of Water Informatics events webpage. And as I said, the recording of today's session will be there in a few days as well. So thanks again, and we hope to see you next time. Bye.
Thanks, everyone.
Thanks.
Thank you.